Hello students! So we are continuing today on stoichiometry, module number 8. We are going to take up example number 3 and we are going to talk about limiting reagents and yields. Okay, example 3. It's getting a little bit more complicated. Now phosphorus trichloride is prepared by a two-step reaction. HCl reacts with manganese oxide to give manganese chloride, water, and chlorine. Phosphorus reacts with chlorine to give phosphorus trichloride. The question is, how many moles of phosphorus trichloride will be prepared from 0.2743 moles of HCl, excess manganese oxide and excess phosphorus? So we're going to follow steps to answer this question. First, we identify what we're looking for. Here is phosphorus trichloride, and what we know. It's the HCl that we know. Then we identify the intermediate that is produced in the first step of the reaction to be used in the second step of the reaction. So the first reaction gives us manganese chloride and chlorine. The second reaction uses chlorine to give PCl3. So here we see that HCl gives PCl3 through the intermediate chlorine. It's produced in the first equation and it's consumed in the second equation. Then it's going to be a little bit complicated, or at first we feel it's complicated. We're going to convert the moles of what we're looking for to the mole of the intermediate, then the moles of the intermediate to what we know using the stoichiometric ratios of the balanced equation. It sounds complicated. It's not as bad as it sounds. We are going to start with the second equation. So if we look at the second equation first, what we're looking for is phosphorus trichloride. The intermediate is chlorine. Remember, we always want to put what we're looking for at the top of our stoichiometric ratio. So we can write the stoichiometric ratio between PCl3 and chlorine. It's 4/6. Now we are looking at our next equation. We can write a stoichiometric ratio with the mole of chlorine over the mole of what we know. Remember, we always want to put at the bottom what we know. So the stoichiometric ratio here is 1/4. At this point, once we have written these two stoichiometric ratios, we can actually combine them. If we multiply this stoichiometric ratio by the second stoichiometric ratio, here is what we get. So we have moles of PCl3 over moles of chlorine times mole of chlorine over moles of HCl on one side. And then this guy here is 4/6. And this guy here is 1/4. So we can now relate the number of moles of phosphorus trichloride to the number of moles of HCl. We can simplify this equation. These two will cancel. So we are left with the stoichiometric ratio between phosphorus trichloride and HCl. It's 1/6. 4 and 4 are canceling each other. So if we now rearrange this stoichiometric ratio to get the number of moles of phosphorus trichloride, it's 1/6 left over on that side times the moles of HCl that is introduced in the reaction. So the number of moles of phosphorus trichloride that is produced is 1/6 of 0.2473 moles of HCl reacted which, if you do the calculation, is 0.04572 moles. So again, you look at your two reactions, you determine which is the reagent that is in common, that is your intermediate, you write your stoichiometric ratios, you combine your stoichiometric ratios so that you end up with a ratio that gives us what you're looking for over what you know, and then you solve. So we're going to introduce the concept of limiting reagent. Let's take a simple example here. Let's assume I am giving you 6 wheels and 2 bike frames. And I tell you, I want you to make bikes with those. Each bike will require 2 wheels, of course. How many bikes can you make? You have 2 wheels, 2 frames, and 6 wheels. You can only make 2 bikes. Your limiting element is the number of frames that you have. You have 6 wheels, 2 frames. So you have an excess of wheels. You will be left over with 2 wheels that you cannot assemble in a bike because you're missing 1 frame. Your limiting piece is the number of frames. In chemistry, it's going to be the same thing. In the examples that we have seen previously, all of the other reagents were given in excess. When it doesn't say that the other reagents are in excess, you should never assume that they are in excess, and you have to determine which is the limiting reagent. In the case I gave you as an example, your number of frames was the limiting reagent. So how are we going to deal with these types of problems? First, we're going to convert all of the reagent masses to number of moles. Then we are going to decide which is the limiting reagent by dividing the number of moles of each reagent by the coefficient in the balanced equation. And then we're going to look at what we get, and we'll see that the smallest number that we get will be the limiting reagent. Now be careful. This is only to determine the limiting reagent. We will always use the number of moles of this limiting reagent, then to calculate the other quantities. And the moles and mass or products that are formed in those reactions will only depend on the number of moles of the limiting reactant. All others are in excess. Let us look at example 4. Sodium thiosulfate can be synthesized by the following reaction. Sodium carbonate reacts with sodium sulfide and sulfur dioxide to give sodium thiosulfate and carbon dioxide. The question is, calculate the maximum mass of sodium thiosulfate. Here it's the molar mass for sodium thiosulfate that can be made by reacting 6 grams of sodium carbonate, molar mass 106.0, 5 grams of sodium sulfide, molar mass 78.0, and 4 grams of sulfur dioxide, molar mass 64.1. So the first thing we have to figure out is which one of the 3 reagents is the limiting reagent. For this, our decision process is going to be convert the masses in number of moles and figure out the number of times the reaction can proceed using the stoichiometric coefficient. So here we write a table with the masses of all 3 reagents, the molar masses for all three reagents, and we calculate the number of moles. So if we look at sodium carbonate, number of moles is 0.0566. Divided by the reaction coefficient, it gives us 0.0566 moles per reagent coefficient, which really is telling you the number of mole times the reaction can proceed based on sodium carbonate. We do the same thing for sodium sulfide. So here we are going to have 0.0641 moles divided by the reaction coefficient. The reaction based on sodium sulfide can proceed 0.032 mole times. If we look at sulfur dioxide, 4 grams divided by 64.1, 0.0624 moles, divided by the reaction coefficient 4, the reaction can proceed, based on sulfur dioxide, 0.0156 mole times. So if we look at these numbers now, we see that the smallest number is actually the number given by sulfur dioxide. So this is now our limiting reagent. So the number of moles of sodium thiosulfate that will be formed depends entirely and only on the number of moles of sulfur dioxide, because it is our limiting reagent. So now to answer the question, we use the reaction coefficient to establish our stoichiometric ratio, number of moles of sodium thiosulfate that is produced over a number of moles of sulfur dioxide is 3/4. Then we know that the mass of sodium thiosulfate that will be produced is the number of moles produced here times the molar mass of sodium thiosulfate. And now I will replace directly the number of moles of sodium thiosulfate here by 3/4 of the number of moles of sulfur dioxide that is used in the reaction. So the mass of sodium thiosulfate that is produced is 3/4 times the number of moles of sulfur dioxide introduced in the reaction, that's our limiting reagent, times the molar mass of sodium thiosulfate. And the answer is 7.40 grams. So again, remember the logic here. We have the masses of all of reagents, the molar masses, we calculate all number of moles, then we relate that to the reaction coefficients. That gives us the number of times, mole times the reaction can proceed based on each reagent, and the smaller number is our limiting reagent. Then all calculations will be based on this limiting reagent and this number of moles. All right, we are going to talk now about reaction yields. So when we have a reaction that involves two reactants, one of which will be a limiting reagent, we will get a product C. The theoretical yield of the reaction will be the maximum weight of product C we can obtain based on the limiting reagent. So in the previous example, the theoretical yield was 7.10 grams. That was the maximum amount of sodium thiosulfate that we could obtain based on sulfur dioxide. Now, life is never perfect. So in fact, we often don't get the reaction going to completion. And we obtain what we call an actual yield. What is the actual experimental weight of product that we have obtained? This is what we call the actual yield, what we actually got from the reaction when we did the experiment. Then the percent yield is what we got, the experimental weight of what we got over the theoretical yield, what we could have gotten in a very perfect world, times 100%. This is our percent yield. We also can calculate a fractional yield. It's the same thing as above, except it's not in percent, so it's the actual yield, what we got, over the theoretical yield. Question for you if you were in class. Can the percent yield be greater than 100%? Can the fractional yield be greater than 1? Remember again, the theoretical yield is what we calculate we will obtain if our reaction is perfect. The actual yield is what we actually isolate from the reaction experimentally. The percent yield cannot be more than 100%. The fractional yield cannot be more than 1 because the actual yield cannot be greater than the theoretical yield. You cannot get more product than the maximum amount of product you calculated from your limiting reagent. So a percent yield is always less than 100. A fractional yield is always less than 1. The closer you get to 100 or the closer you get to 1, the better your reaction, the more efficient your reaction is. Therefore, example 5. In the reaction considered previously, we now have obtained 0.652 grams of sodium thiosulfate. Remember in example 4, we had calculated for that reaction that 4 grams of sulfur dioxide, which was our limiting reagent, would give us a maximum of 7.4 grams sodium thiosulfate. So what is the theoretical yield here for this reaction? It's what we calculated was the maximum amount of sodium thiosulfate we could get. What is the actual yield is what we actually isolated when we did the reaction, 0.652 grams. What is the percent yield and fractional yield? The fractional yield is the actual yield, 0.652, divided by the theoretical yield, 7.40, so it's 0.0881. And the percent yield is the fractional yield times 100, so 8.81%. You see that this is really a very poor reaction. I wouldn't like my students to have such a poor reaction in my lab. So now the question is, how do we go about making 1.2 grams of sodium thiosulfate, assuming the yield obtained here of 8.81%? How much sulfur dioxide do we need to react with excess sodium carbonate and sodium sulfide to actually get this 1.2 grams of sodium thiosulfate? So remember that we have now a ratio that is telling us that 4 grams of sulfur dioxide gave us 0.652 grams of sodium thiosulfate. So we can write this ratio, the mass of sulfur dioxide reacted over the mass of sodium thiosulfate actually obtained is 4 over 0.652. Now, if we want more sodium thiosulfate, we can now rearrange this ratio 4 over 0.652 times 1.20 grams of sodium thiosulfate. This will be 7.36 grams of sulfur dioxide. So in order for us to get 1.2 grams of sodium thiosulfate, based on this very poor efficiency, we need to put into the reaction 7.36 grams of sulfur dioxide, much more than the 4 grams that we had involved in the reaction in the first place. Example 6. What volume in milliliter of 10 molar HCl solution is needed to prepare 2 grams of chlorine based on the following reaction and assuming excess manganese oxide? So this is the reaction. 4HCl plus manganese oxide gives manganese chloride plus chlorine plus water. We write what we know and we write what we want. So we want 2 grams of chlorine, molar mass 70.906, and we are using a solution 10 molar of HCl. We need to find out what is the volume of this solution that we need to use. So the first question is, what is the stoichiometry between HCl and chlorine? This is what we know. This is what we need to find out. So number of moles of HCl over chlorine is 4 over 1. So that is the stoichiometry for this reaction. If the reaction is 100% efficient, how much HCl do we need? So then the number of moles of HCl is 4 times the number of moles of chlorine that we need, which is found in 2 grams of chlorine. So we plug in the number of moles of chlorine is the mass of chlorine over the molar mass of chlorine. Plug in the number, we want 2 grams, molar mass 70.906, so it's 0.0282 moles. So the number of moles of HCl that we need is 4 times this, based on the stoichiometric ratio, so it's 0.113 moles. So remember that the number of moles of HCl is what we need to find in a given volume of HCl, and that's what we're after. So remember your equation, number of mole of HCl is the concentrations times the volume. We're after the volume, so rearranging this equation, number of moles of HCl over the concentration of HCl, 0.113 moles divided by 10 moles per liter. So we're going to have a volume in liters. The volume of HCl that we need is 0.0113 liters, or 11.3 milliliters of 10 molar HCl. Now, in fact, the reaction is only 31% efficient. So when we reacted our 11.3 milliliters of HCl solution, the theoretical yield was 2 grams. If the reaction is only 31% efficient, it means that the percent yield is 31%. So how much chlorine did we get? The percent yield, remember, is the actual yield over the theoretical yield. Here we are told that is 31%. So the actual yield of chlorine, if the reaction is only 31% efficient, is the percent yield times the theoretical yield of 2 divided by 100. So 31 times 2 divided by 100, we only got 0.620 grams if the reaction was only 31% efficient. not the 2 grams that we wanted. So here we're going to use the same ratio to figure out how much HCl we need to actually use to get the 2 grams that we want. So 0.62 grams of chlorine was obtained or would be obtained for 11.3 milliliters of HCl. We have the ratio, the volume of HCl reacted over the mass of chlorine actually obtained is 11.3 times 0.620. So now what do we need to react to actually get 2 grams? This ratio will remain constant. What we need to react is 11.3 divided by 0.620 times the 2 grams of chlorine that we want. So the volume of HCl that we need to use if the reaction is only 31% efficient is 36.5 milliliters. That will ensure that 2 grams of chlorine is actually produced. Okay, so this concludes Module A. This was a little bit longer than usual because we had to go slowly through the calculations. Make sure that you practice on these concepts. Play the video multiple times to really grasp the concept that we saw. Go and do activity 8, and I will see you soon. Bye now.